All right, today we're going to start going a little bit deeper because up until this point, I've been telling you some simplifications, some things that are not quite 100% true. And one of those simplifications is this idea that the number of protons and the number of electrons in an atom are going to be the same. That's true if we're talking about a neutral atom. But in nature, we don't always end up with neutral atoms. Oftentimes, we end up with these things called ions, I-O-N-S. And these ions are what happens when an atom gains or loses an electron or electrons and thus becomes charged. So today, what we're going to be doing is we're going to be working to understand the difference between an atom, which is neutral, and an ion, which has a charge. We're going to try to understand how and why atoms are going to either gain or lose electrons in order to become stable by having a full outermost electron shell. So we're going to be paying a lot of attention to that valence shell, that outermost electron shell. That's why you have the ability to draw things like these Lewis structures that really highlight, oh, these are the valence electrons. And we want to be able to figure out the charge of an ion, how positive or how negative it's going to be. Now, in chemistry, you're going to hear me talk a lot about like, oh, the atoms want this, or they're trying to do that. And I want to be really clear. Atoms are not sentient. They have no minds, no desires, no wants, no will, no hopes or dreams. Okay? The word want here does not refer to an actual sense of desire. Instead, it's describing a thing that happens. And the thing that happens is that if something is unstable, it's going to be in a constant state of change. But if something is stable, it's going to stay that way. So in nature, what oftentimes ends up happening is you'll have something that's unstable, and the unstable things will alter, they'll change, until, just by random chance, they manage to hit a configuration that is stable. And once something hits a configuration that's stable, it's going to stay that way. Imagine if you know, like, oh, there's going to be a lunch club happening in so-and-so's classroom, but you have no idea what the club is. If you walk into that room, and you come in and it's like, oh, this is anime club. A bunch of kids are in here watching anime, and you like anime, you're going to stay in that room. But if you don't like anime, you're going to leave, right? What you end up with is a stable configuration, which is a room full of kids who like anime, right? Even though it's totally random who walks into the room. It's just that if it's a stable situation, you're going to stay that way. If it's an unstable situation, you're going to leave, right? And so what ends up happening is chemistry is this weird mix of like totally random events that end up with really deterministic results. There's no one who's trying to do anything. There's no desire, there's no will, there's no goals. Things are just happening until, completely by random chance, we end up with a configuration that is stable. And that stable configuration is going to stick around. So in nature, if I look at a bunch of ions, I can predict for any given element, oh, this is exactly what your ion's going to look like. Even though there's nothing to stop it from gaining or losing electrons willy-nilly. It's just that they're going to be doing that until they hit the right configuration. And once they hit that right configuration, they're going to stay that way. So even though there's no goal, there's no will, there's no intentionality, we still end up with really predictable results. So we have random things that are happening, but really predictable things that we're going to end up with. Okay, so what I'm going to teach you is how to understand what's the predictable, stable outcome that's going to stick around. And if you look around in nature, what you're going to find is the stable outcomes. That's going to be what actually sticks. Because if it wasn't stable, it would keep changing. Does that make sense? Feel okay with this? All right. So, the thing that makes an atom stable and happy, again, happy here is just a word that means it's not going to be changing anymore, they don't have emotions, is having a full outermost electron shell, a full shell of valence electrons. So for those things in columns 1A through 8A, that segment of the periodic table that we're going to spend most of our time studying, a full outermost electron shell means 8 valence electrons. Or, alternatively, going down to 0, in which case the next shell in is the full shell. Right? So 8 or 0 valence electrons, that is this thing that's really stable, that's going to stick around and continue to exist. We call this desire, again, not a real desire, but I'm using those words. We call this desire of atoms to get to this stability of either 8 or 0 valence electrons, the octet rule. O-C-T-E-T. Octet means 8. Now, atoms that have gained or lost electrons aren't going to be neutral anymore. Because the whole reason why we say that atoms are neutrally charged is because every proton has a charge of +1, every electron has a charge of -1. So for a neutral atom, you have the same number of positive charges and negative charges. Yeah?
Can you spell the word again?
Octet. O-C-T-E-T. So O-C-T-E-T.
And what's
So
the
the
stop
octet rule says ions want 8 or 0 valence electrons. So today we're going to be learning about these ions. So, atoms are going to gain or lose electrons, and as they do this, they can become stable. So let's look at sodium here. So sodium has 11 protons. Having 11 protons is the thing that makes an atom sodium. It's element number 11 on the periodic table, its atomic number is 11. So for a neutral sodium atom, it also has 11 electrons. And if we think back to our planetary models, we know that means 2 in the first shell. Okay, then the first shell's full. We move to our second shell, 1, 2, 3, 4, 1 in each quadrant, 5, 6, 7, 8. Now the second shell is full, so that's 10 electrons. And then we can move to the third shell, 1 last electron. So 11 electrons total. For sodium to follow the octet rule, to get to that either 8 or 0 valence electrons, there's 2 ways that this could happen. It could either gain 7 electrons, or it could lose 1. Which of those do you think is an easier thing to do? Gaining 7 or losing 1? Losing 1, right? If you imagine just like people randomly walking in and out of a room, it's way more likely, but the door locks as soon as you either hit 8 or 0 people. If you had one person in the room and it's just like random, whether somebody walks in or out, you're gonna hit 0 way more likely than you're gonna hit 8. Okay? So that 1 electron, the moment it ends up leaving, the thing becomes stable and it stops changing. Then we have what's called a sodium ion. I-O-N, sodium ion. And now you can see, oh, this sodium ion, it has a full outermost electron shell. This is one of the reasons why I'm so picky about how we place our electrons, because you can look at this at a glance and see this electron shell is full. Whereas if the electrons are scattered around a circle, it's really hard to tell the difference between 7 and 8. But here I can be like 2, 4, 6, 8. Great, that's full. So when it does this, now there's no third shell, because there's no electrons in the third shell. So its outermost shell is now the second one, and that outermost shell is full, so it's stable, and it's going to stay that way. But now something has changed. We had 11 protons and 11 electrons to start, but we lost an electron, so now we have 11 protons and 10 electrons.
So the charge is +1?
So the charge is now +1. Electrons are negative. If you lose an electron, that's like subtracting a negative number. Y'all are doing negative numbers in math, right?
Yeah, we're using cold and hot cubes.
Yeah. So it's like taking out a cold cube. In that, so not as a metaphor with like you've got a bowl of soup,
Yeah.
right? And you can either add a hot cube or you can add a cold cube, right? It's like taking a cold cube out of the pot of soup. The soup's gonna get warmer,
Yeah.
right? The electrons are the cold cubes and the protons are the hot cubes, right? So the protons are positive, the electrons are negative. If you take out an electron, you become more positive. Yes?
Wait, so it could either gain 7 or lose 1?
It could either gain 7 or it could lose 1 in theory, but whether they gain or lose electrons happens randomly. And when it's just like random chance, you're way, way, way more likely to end up hitting 0 than you are to end up hitting 8. And as soon as you do hit 0, you stop changing. So in nature, you're pretty much always going to run into sodium ions with a charge of positive 1. Yeah?
Can you lose protons?
No, not in the same way. So remember that protons and neutrons are in that core, that heart of the atom. They're all like tucked in a tight bundle, while the electrons are all in the electron cloud. They're just kind of zipping around, right? So you can't really lose something from right here, but these things, which in reality aren't in a pretty perfect little ring, they're actually in a cloud where they're zipping around all over the place ultra fast. It's very easy for atoms to gain or lose an electron. Yes, Helen?
So in theory, if you gain 7 electrons, it would have a negative charge?
Yes, in theory. But you almost never see something gain or lose a huge number of electrons. Usually it's going to be either like gaining or losing 1, 2, or 3. We don't tend to see really large charges. All right. Something else I want to point out here. You'll note right here, so Na stands for sodium. This plus right here means it's got a charge of +1. A thing I've said to you before is that chemists are really lazy in certain ways. In any system, there's certain assumptions that are kind of baked into the grammar of it. So for example, mathematics has a grammar. If you want to write 5 plus 5, what you actually mean when you write 5 plus 5 is positive 5 plus positive 5. Right? When you write 5 plus 5, oh, that's a dead marker. If you write 5 plus 5, what you actually mean is positive 5 plus positive 5 equals positive 10. But in math, like in Nat's classroom, you're not required to write this positive in front of all your positive numbers, right? Because it's so much more common to run into positive numbers. So in math, you can be lazy and you can just say 5 plus 5 equals 10. And this is perfectly fine. Even though what it really means is this. In chemistry, there's a different set of things that are really common that we want to be careful about. Or there's a different set of things that are really common and so we can sort of ignore. Things having a charge of +1 or -1, or there being a single atom in a molecule, a single atom of a specific element in a molecule is really common. So in chemistry, we typically don't bother writing the number 1. So here, when that sodium says Na+, what that plus really means is +1. So if something has a charge of +1, we don't have to write out that 1, we can just write a plus. If something had a charge of +2 or +3, then I would write the +2 or the +3. Likewise, when we're talking about chemical formulas, think about, H2O. I specify that there's 2 hydrogens, but I didn't specify that there's really only 1 oxygen. This is what H2O really means. It really means H2O1. It's just that for chemists, because there being one of something is so common, we don't have to bother writing that. We can just write H2O. In the same way that in a math class, you don't have to write a plus in front of every positive number, because you kind of assume that a number is positive unless you specify that it isn't. Yeah. There's a lot of hidden grammar to all the things you do. There's certain assumptions that are baked into everything. In chemistry, we just have a slightly different set of assumptions than you have in a math classroom. All right. So let's talk about how you figure out the charge of an ion. If you want a really simple formula and you don't want to think about positive and negative numbers, you could use the formula the number of protons minus the number of electrons. So the number of protons minus the number of electrons equals the charge.
Right, so this is to find the charge of an ion.
That's to find the charge of an ion. So for the example I just gave you with a sodium ion, that sodium ion had 11 protons and it had 10 electrons. So 11 minus 10 equals positive 1. Or, in chemistry, you can just say plus. The reason why this works, if we want to be a little bit more specific, a little bit more accurate, if we want to pull in your understanding of negative numbers, is what's really happening is all those protons have a charge of plus 1. So we have 11 positive charges. And then we also have every electron having a negative charge. So we've got 10 negative charges there. So remember that sodium atom lost an electron to become a sodium ion. So positive 11 plus negative 10 equals what? Positive 1. Which again, in chemistry, we can just write as plus, because we assume we learned. So you can either think about this using positive and negative numbers and be like the number of protons, or the number of charges from the protons, plus the number of charges from the electrons. Or you can just say number of protons minus number of electrons is the charge. Given that you're thinking about negative numbers in math right now, I might recommend thinking about this, because it is a really common application of the stuff you're learning right now in math. All right, what this means is that if you're gaining electrons, that means that you are adding a negative. So things that gain electrons have a negative charge. And we have a special name for those ions. We call them anions. A-N-I-O-N-S. I like to think of it as like a negative ion. Now, if you are losing electrons, that means you're subtracting a negative. In the lesson that you have in math, thinking about like the hot cubes and the cold cubes in the bowl of soup, if you take out a cold ice cube, you're subtracting a negative, soup gets warmer, right? So subtracting a negative makes you more positive. So if you're losing electrons, then you become positive. We have a special name for positive ions. We refer to them as cations. And if you are ever having difficulty remembering whether cations are positive or negative, I just want to remind you that cations are positive.
Oh.
And if you think that pun wasn't very funny, then I have terrible news for you, which is that I'm going to run through that pun 1,000 times more until it is burned into the back of your brain, so that someday, years from now, when you are in a high school chemistry classroom taking a vocab test, you'll sit there and you'll be like, all right, the cat. And you'll have the answer still there, stuck in the back of your head forever.
It's already burned into the back of my brain.
Yep. All right. So we've got positive cations and negative anions. All right, so let's take a moment and just reiterate. Think about the charge of a sodium ion. Sodium is the atom with 11 protons. We've got positive 11 here. If we have 11 electrons for the neutral atom, then positive 11 plus negative 11 equals a charge of 0. But here for the ion, where we've lost that electron has gone away, we still have 11 protons, because having 11 protons is what makes this sodium. But now there's only 10 electrons, so you could either think of this as 11 minus 10 is positive 1, or you can think of it as positive 11 charges from the protons, plus negative 10 charges from the electrons gives us a net charge of positive 1. There's a lot of little background convo, and I'd love it if we could bring that under control. All right, so let's try another. This is chlorine. So chlorine has 7 valence electrons. It's in column 7A. With 7 valence electrons, electrons to fulfill that octet rule, to become stable, it could either lose all 7 valence electrons, or it could gain 1 electron. Which do you think is going to end up happening?
It's gonna get the electron.
It's going to end up gaining 1 electron. So we're adding 1 negative. We're taking 1 ice cube, sticking it in the bowl of soup. So chlorine gains an electron to fill that outermost electron shell. A chlorine ion is now going to have 17 protons, but 18 electrons. So there we have positive 17 plus negative 18, which gives us a charge of what? Negative 1, which we can just write as a minus sign, because chemists are too lazy to bother writing the number 1. We still say it out loud, we don't write it. Yossi?
It can't ever be. It can't ever be like -2 or anything. Right?
So
Or
a
if it
chlorine
is-
ion wouldn't ever be -2, but let's look at another example. Let's take this sulfur. All right, so this is sulfur. How is this sulfur going to want to gain or lose electrons? Raise your hand if you think you can answer for me. Lisa?
It's gonna gain 2 electrons.
Yeah, it's going to want to gain 2 electrons. So 1 electron's going to come in here. 1 electron's going to come in here. On today's assignment, you're either going to be filling in or crossing out electrons on a picture like this. So this sulfur, if it gains 2 extra electrons, we added 2 negative charges. So what would the charge of this one be?
+2.
We're gaining negatives.
Oh, -2.
Yeah, so the way I would write that ion is an S for sulfur and then -2. You'll also see this written as, some folks will write 2 minus versus -2. I'm not going to be picky about which way you do it. I've seen it done both ways from reputable sources. So you're welcome to use either of these. It's just a little bit of grammar. Think of it like an accent that certain chemists have. Some people write it like this. Some people write it like this. Naya?
What if you have like 4 on the 4 valence electron?
Oh, that is such a delightful question. So for an atom like carbon with 4 valence electrons, they tend not to make ions. So not every atom likes to make ions. What I'm saying right now, I'm going to be really clear, is an oversimplification. When you get into really way more complicated setups for where the electrons can be, right now we're kind of mostly focusing in on the A groups, right? Those 2 columns on the left, the 6 columns on the right. Broadly speaking there, we're not really going to be making +4 or -4 ions. And also, that thing I just said is a lie. It's a gross oversimplification. There are ions with a charge of +4 or -4. It's just way more complicated, and the model that I'm giving you right now doesn't explain why it happens. So that's a question you're going to just have to acknowledge is going to sit with you until high school chemistry. And then maybe you can get into, when you learn a more complicated way of arranging the electrons, is when you'll be able to get that answer. Yossi?
So you would only just write the element symbol and then minus when it's a negative charge of 1.
Yes, exactly.
But every number after that, you write the number.
Yes.
Okay.
Yes. So for chlorine here, so chlorine, Cl is its symbol. And that's a chlorine with a charge of -1, so I write Cl for chlorine, and then just a minus to show that it has a charge of -1. All right. So here's how we, just to reiterate that, here's how we write the charges of ions. So sodium has a charge of +1, so we write Na+. A chloride ion has a charge of -1, so I just write Cl-. A magnesium ion likes to lose 2 valence electrons, so it ends up with a charge of +2 because we're subtracting 2 negatives. So magnesium ions are +2 or 2+. And oxide ion, so when an oxygen forms an ion, it likes to gain 2 electrons, so it has a charge of 2-. I also want to take a moment and talk about another sort of weird bit of chemistry grammar, because where this is going is we're going to start talking soon about ionic bonds. How these ions can come together to form chemical compounds. And we're going to need a way to name those chemical compounds. So the name of an ion is going to vary depending on whether it's a positive cation or a negative anion. The names for cations are exactly the same as the name of the atom, right? So a sodium cation is just called a sodium ion versus a sodium atom. The names for anions, for our negative ions, you'll notice a really specific little grammatical thing that happens to them. You'll notice, do y'all see how a bunch of the elements on the periodic table end in like I-N-E?
Yeah.
Like chlorine, fluorine, right, etc. We take the sort of end of the word and change it into IDE. So chlorine becomes chloride. Fluorine becomes fluoride.
Oh, like the stuff they put in our water?
Yeah. And this will even happen for the ones that don't end in INE. So for example, oxygen becomes oxide. Nitrogen becomes nitride. So the name of an anion, we just like lop off the second part of the element name and replace it with IDE. Yes?
I forget what I was going to say.
All right. Whew. And then when we want to talk about a chemical compound, if you've got an ionic compound, something that's made out of a cation and an anion, it's just name of the cation followed by name of the anion. And we'll give an example of that shortly. So, the big thing that we've learned today is that atoms will gain or lose electrons in order to fulfill this octet rule and become stable by having a full outermost electron shell. This creates one form of stability. It also introduces a new instability because now it has a charge. It's not neutral anymore. It's a tiny magnet. So a sodium cation with a charge of +1, that's like a little positive pole of a magnet. A chloride anion with a charge of -1, that's like a little negative pole of a magnet. And a positive and a negative, they're going to snap together. Just like if you've got two magnets, they'll snap together with the positive pole and the negative pole. Right? So there's a new form of instability that's introduced, and ions can deal with that instability by joining up with another ion with its opposite charge. So for example, Na+ and Cl-, sodium and chloride, those can snap together to form a chemical compound, which we would call sodium, the name of the cation, chloride, name of the anion. So name of the cation, then name of the anion, sodium chloride. You'll notice in the chemical formula, we'll talk more about chemical formulas tomorrow, we have the name of the cation, followed by, or the cation comes first, then the anion. Now, in reality, it's not just going to be a single sodium and a single chlorine, because all of chemistry is happening at scale. What you would actually end up with is a lattice of positive sodium cations and negative chlorine anions all clicked together. A lot of ionic compounds will form crystals because it's just like an endless repeating pattern of the cations and the anions. I am going to require a little bit of camera work for you, so go ahead and pick that up just to show this last thing. If you look up here, you can see an example of a salt crystal. This crystal is huge. It's just an endless array of positive sodiums and negative chlorides, all linked together to make this big old salt crystal. And on that note, that's all I have for you today.